We have talked about a density. Now, what is the most general form of a density? The answer turns out to be surprisingly complicated. We shall discuss this at length when we shall learn about a concept called the Lebesgue integral. But for now, we shall restrict our attention to only a special class of densities that occur in almost all real-life problems, and such densities are supported on some interval in the real line, which I call I, and the density vanishes outside that interval and is positive inside that interval. And over this interval, it is also Riemann integrable. In case you are scared of the term Riemann integrable, it is just our usual integration that we learned during our higher secondary days. Actually, in most cases, it is not just Riemann integrable, it turns out to be continuous. So once I restrict my attention to functions that vanish outside an interval and is strictly positive inside the interval and is Riemann integrable or even continuous, then in that restricted class, it is quite easy to give the general form of a density. We shall state it in the form of a theorem. We shall start with an interval I, and we shall consider a function defined from R which vanishes outside I and is strictly positive over I. And we shall also assume that f is Riemann integrable. Riemann integrable over I or over entire R doesn't matter because it vanishes outside I. And when I say Riemann integrable, I mean in the improper sense because R is unbounded. Then this f is a PDF if and only if the total integral is 1. Now we have already seen this implication. If it is the density of a random variable, then we have seen that this must hold. Now I am making the reverse claim also. If this condition holds, this together with the fact that it is a non-negative thing, then it must be a density. So there must exist a random variable with this f as the PDF. Now we shall prove this soon, but first let's take a look at some examples. Our first example is fx equals 3x squared if x is in 0 to 1 and 0 otherwise. The graph looks like this. You must understand that fx always is defined over entire R. So the graph actually extends like this and this. In this case, our supporting interval is this 0, 1. This is our supporting interval and it is just here. And I have said 0 else. Why is it a density? Because if I consider the entire integral, the entire area under the curve, of course these parts do not contribute anything. So if you just integrate under this, you will see that the total area turns out to be 1. I always start with the full integral from minus infinity to infinity, which reduces to integrating only over the supporting interval. And that after a few steps will give you 1. So this is a density. It is always non-negative. In this example, the supporting interval is bounded. It could as well be unbounded. It is 2 times e to the power minus 2x if x is from 0 to infinity. So our supporting interval is now this. You must remember that it is defined over entire R. So it's not just this part. This is also part of the density. And if I try to check whether it's the density, I will integrate from minus infinity to plus infinity, which will actually reduce to finding this area, which after some manipulation will turn out to be 1. So this is also a density. Here is a more complicated example where the supporting interval is bounded, but the function itself is unbounded. It is going towards infinity in both these points. This is non-negative, and if you integrate it, you will find that the total integral is 1, though the integration in this case is not that simple. Now here is one yet more complicated example where the supporting interval itself is unbounded. It is 0 to infinity, and the function also is unbounded. It is going towards infinity up there, and you can check that this total integral is 1, but that is again not very easy owing to the nature of the integrand. But it is possible to show that the total integral is 1, and of course it's a non-negative function, so it is a density. So this gives you an idea of the different types of densities that we can get even in our restricted class, where the things are supported over a single interval and it is continuous. Find a constant c in R, if that's possible, such that this function is a density. Observe that in this case the supporting interval is entire R. So your job is to check if such a c is possible, and if so, to find it.